Hello everyone, I am Shanmugavel from Madras Institute of Technology, Anna University campus, and our team QuibitX is going to present a solution for quantum optimized multi-sensor fusion for stealth target detection. So now let us see about our problem statement and other things. So first, the challenge that we are facing is the modern stealth aircrafts and low signature drones are becoming increasingly difficult to detect using conventional radar systems alone. Our project addresses this challenge by combining information from radar, thermal, infrared, and acoustic sensors using intelligent sensor fusion, followed by quantum inspired optimization and AI based target classification. So, instead of depending on a single sensing modality, our solution combines four complementary sensors so that the strength of one compensates for the weakness of another. Our flow begins with sensor acquisition and followed by pre-processing and future extraction. The information is then fused using the optimal fusion algorithm, optimized using quantum techniques, classified by an AI model, and finally visualized through a real-time dashboard. So now let us see about our sensor fusion methodology. So in this thing, we have evaluated three different sensor fusion strategies like Wade fusion, Bayesian fusion, and Kalman fusion. Rather than selecting an algorithm based on theory alone, we experimentally compared all the three approaches. Our evaluation showed Wade fusion achieves approximately 53% detection performance and Bayes fusion achieved approximately 54% and Kalman fusion achieved approximately 81% and making it the best performing approach. The Kalman fusion was selected because it continuously estimated the true target state and suppresses sensor noise and predicts the target motion and performs efficiently in real-time environment. So after the fused features are passed to the random forest AI classifier, the complete system achieves a final classification accuracy of 88.8%. And before this random forest AI classifier, we only achieved the 81% of the performance. So now let us see how we are going to implement the quantum optimization data. So the traditional AI models often rely on manually tuned parameters which may not produce the optimal solution. To overcome this limitation, we introduced the quantum optimization. So our optimization focuses on three components, the sensor fusion weights and future selection and random forest hyperparameters. We formulate this optimization problem as a quadratic unconstrained binary optimization or QAOA problem. We then solved it using the quantum approximate optimization algorithm like QAOA through the QSkit simulator. Since the computation's quantum now hardware is only available during the event, we designed a modular quantum optimizer interface that can seamlessly transition from simulation to real quantum hardware in the future. So now let us see about the detection performance, how it is going to detect. So in this, our model achieved 88.8% overall classification accuracy and 97.9% detection rate and low false alarm rate. So the ROC curves demonstrate strong discrimination across all the 9 target classes, while the confusion matrix shows the consistent classification performance with only limited confusion between similar categories. The false alarms class remains the most challenging, which represents an opportunity for future environment. So let's go to the sensor contribution analysis. So this slide demonstrates why combining multiple sensors is essential. We performed an incremental fusion analysis using the F1 score, which balances precision and recall. We observed that the thermal sensing contributed the largest improvement, infrared provided additional robustness, and acoustic sensing further improved discrimination. Overall, 4 sensor fusion increased the F1 score by approximately 14 points compared to radar only detection. This validates that each sensing modality contributes the complementary information to the final decision. So the main part of the program is we have developed some prototype of initial stage. Whatever the concept that we have done so far, we have implemented in the real-time prototype. So for this project, you can explore our GitHub page for seeing the details of our project. And at the ending, we'll also explain these projects. So finally, The impact and future works of our project will be it can be used in defense and airspace surveillance and border security, search and rescue, and critical infrastructure protection. Currently, our system has been validated using a synthetic multi-sensor dataset, and quantum now hardware validation remains future work. In the next phase, we plan to integrate real sensor datasets, deploy the optimization and quantum now hardware, improve false alarm discrimination, and implement the complete system on the edge AI platform for real-time deployment. We believe our approach demonstrates how AI sensor fusion and quantum optimization can be combined to create more reliable and intelligent surveillance system. Thank you. We would be happy to answer any questions. So at the ending, we will also see about the prototype demonstration with this video. So thank you. Now let us see about our prototype demonstration with this video. So this is our proof of concept command center, and it provides an integrated view of the mission, sensor status, and AI predictions. It demonstrates how operators would interact with the system. So now let us go into the live mission demonstration. So this demonstration, our current simulation environment, we generate the synchronized outputs from radar, thermal, and infrared and acoustic sensors, fuse the observation, and classify the detected targets using our AI pipeline. So next, let us see about our fusion comparison. And one of our completed engineering studies was comparing multiple fusion strategies. We evaluate Wade, Bayesian, and Kalman fusion. Based on these assessments, Kalman fusion provides the extraordinary simulated environment, so it forms a basis of our current proof of concept. So the quantum optimization. So for the pre-selection stage, we designed and validated a quantum optimization workflow using a Acoustic air simulation architecture is modular, allowing the optimizer can be replaced with the computation quantum now platform during the final hackathon. Our objective in the 36-hour hackathon will be to validate this workflow on the target quantum environment and quantify the performance gains. So the model evaluation, these results represent the current performance of our proof of concept using our synthetic dataset. During the final hackathon, we plan to expand the evaluation with larger datasets and further optimize the model. So this proof of concept demonstrates our architecture is technically feasible. If selected for the final round, we will focus on integrating the computation's quantum platform, strengthening the optimization process, validating with larger datasets, and further improving system correctness. So thank you for giving this opportunity. We are grateful for your opportunity. So thank you all.